Welcome to the Explainer. Today, we're going to go on an infinite journey to solve a puzzle that has fascinated thinkers for literally centuries. And to do that, we're going to have to get to know one of the most fundamental ideas in all of calculus, the sequence. So, let's start with that puzzle. Can you get infinitely close to something without ever actually touching it? I mean, that sounds kind of impossible, right? Like some kind of paradox? But stick with me, because by the end of this explainer, we'll have the exact mathematical tools we need to solve it. All right, so to even start tackling our puzzle, we've got to meet the main character of our story today, the sequence. It's really the key to unlocking this whole idea of an infinite journey. So what is a sequence really? Well, formally, it's a function that maps natural numbers to real numbers. But yeah, let's just cut through all that jargon. The best way to think about it is just as an infinite, ordered list of numbers. That's it, an endless journey with an infinite number of steps. Let's take a look at a classic example, the sequence 1 over n. Its journey starts at the number 1, then its next step takes it to 1/2, then 1/3, then 1/4, and it just keeps on going like that forever. Each step gets smaller and smaller, sure, but the journey never actually ends. So where is it going? Okay, so if this journey just goes on forever, where can it possibly go? I mean, does it just fly off towards infinity? Or are there some kind of rules of the road that keep it contained? Let's find out. And that brings us to a really crucial idea, boundedness. The best way to think about it is like a fence. A sequence is bounded if its entire infinite path, every single step it's ever going to take, stays inside that fence. It just can't escape. And here you can see two totally different kinds of journeys side by side. On the left, you've got this sequence that bounces back and forth. But look, it's completely trapped between -1/2 and +1/2. It's bounded. But on the right, whoa, that sequence just explodes. It jumps from -2 to 4 to -8, getting farther and farther away from 0 with every single step. It is totally unbounded. And, we can get even more specific with these rules. A sequence might be bounded only from above. Think of it like a rocket that has a maximum altitude it just can't pass. Or it could be bounded only from below, kind of like a submarine with a maximum depth. A sequence that we call simply bounded is one that has both a ceiling and a floor. So, knowing if a journey is contained is useful for sure. But that's not the whole story, not even close. The really interesting question, the one we're all here for, is this. Does the journey actually lead anywhere? Is it headed for a final destination? And it turns out, yeah, some of these sequences, even with their infinite number of steps, are actually heading towards a very, very specific point. With every single step they take, they just inch a little bit nearer to this destination. They're constantly closing the distance, narrowing that gap between where they are and where they're going. And this is the most important part. They don't just visit the destination and then leave. No. After a certain point in the journey, they get so close that they stay within any tiny distance of it you can possibly imagine. Forever. So this whole idea, getting infinitely close and staying there, that's what mathematicians call a limit. Imagine you draw a tiny little target around the destination. Well, if a sequence has a limit, it means that eventually all of its steps are going to land inside that target no matter how small you make it. When that happens, we say the sequence converges. And this brings us to one of my absolute favorite tools for finding limits, the sandwich theorem. Seriously, it's as cool as it sounds. Picture this. Your sequence is the delicious filling in a sandwich. Now, if you know that the top and bottom pieces of bread are both heading to the exact same spot on the plate, then the filling in the middle, it has no choice. It has to go there too. It's this beautiful, logical trap that gives us absolute certainty. All right, now for the big payoff. We don't always have to check every single sequence from scratch. Mathematicians have come up with these incredibly powerful theorems that act as guarantees. If a sequence follows certain rules of the road, we know something amazing about its destination without even having to calculate it directly. So what in the world does that mean? Well, this is the guarantee. If your journey is bounded, if it stays inside those fences we talked about, then at least part of your journey is heading to a specific destination. Think about it. Even if the whole journey is just kind of bouncing around, you can always find a smaller, more focused journey inside of it, a subsequence, that is heading somewhere specific. The whole sequence might not converge, but a part of it is guaranteed to. And what's really cool is that these destinations, these limits, they behave in a super predictable, super friendly way. If you have two sequences and you already know where they're going, you can find the destination of their sum, their product, or their quotient just by doing the same math on their limits. It works exactly how you think it would. A journey to 5 plus a journey to 10 results in a combined journey to 15. It's simple and it's powerful. So let's just take a breath and recap the journey we've been on in this explainer. We started with this idea of a sequence as an infinite path. We learned how to tell if that path is contained with the concept of boundedness. And then we discovered how to find its ultimate destination using the incredible idea of a limit. And look, this isn't just some abstract math game. This concept, getting infinitely close to a value, is the absolute bedrock of calculus. And calculus helps us